So I have a question for you. Would you fly on an airplane if the airplane was not simulated first in a computer? In the same way, Hans Lerach, a celebrated scientist from the Max Planck Institute in Berlin, asked, would you want to be treated with a therapy which has not been carefully tested on your virtual twin? So my name is Sharan. I'm from the School of Computer Science, and my mission is to build a disease simulator that for any individual with a disease will be able to predict the outcome of any therapy for this disease so that we are able to choose the best one. Over the past 5 years, I developed, together with my group, a unique prototype of such a simulator, which we call ANAT, Advanced Network Analysis Tool. And this tool has been already downloaded by hundreds of labs worldwide and is used by leading labs in Harvard and Berkeley for disease simulation. And to tell you a bit how it works, let me go back to the analogy of airplanes. So suppose you want to simulate an airplane in a computer. What you need is a list of components of that airplane and a map of connections, or we call it a network between them. Now, if some components malfunction, you can locate their location in the network and try to trace their influence. Very similarly, when you want to simulate the cell of an individual, what you need is a list of components. These are the genes of the individual, and a map of connections or a network between them as the network that is shown here. Now, additionally, you need some information on genes that are malfunctioning or misbehaving in the disease condition. Now, the output of ANAT is a model centered around those genes and allows us to understand how they connect together, what is the logic of the connection together to make up the disease. In order to do that, ANAT has to do two things. It has to somehow locate in this very complex network this region that is responsible for the disease, and it has to model the activity of every gene in this model, in this tiny model that it produces as a function of the activities of the other genes. Now, in order to show you the utility of ANAT in the real world, let me share with you a recent collaboration with the lab of Gil Ast from the medical school, in which we tried to simulate colon cancer. In this case, the Ast lab collected from public databases dozens of genes that were shown to misbehave in colon cancer. These are the blue genes that are shown here. However, they did not understand how these genes connect together to make up the disease. When we applied ANAT to this set of genes, it came up with this very focused model that explains how these genes go together. And further, it highlights a very interesting and novel pathway of 3 genes that are shown here, ELK1, CMYC, and PTB, that the model predicts that their overactivation leads to many of the misbehaviors or observed changes in the disease. In order to test this now very focused hypothesis raised by ANAT, the Ast lab manipulated cells so that they overactivate the first gene in this chain. And what they observed is that, like in a domino effect, it led to the activation of the second gene, the third gene, and eventually to all the predicted changes. Now, to see whether this finding that was done in the lab also translates to the real world, we took advantage of the fact that we had access to samples from real colon cancer patients. And what we did was to measure the levels of these 3 genes in those patients. What we found out is that for 2/3 of the patients, the 3 genes, this pathway that was predicted by ANAT, were significantly elevated in the tumor tissues shown in red compared to the normal tissues of the same patients. So what it means is that for these 2/3 of the patients, the 3 genes are probably driving the disease, and by targeting them with a drug, we may be able to fight the disease. While for the other 1/3 of the patients, probably targeting those genes will not have any substantial effect. So imagine now a world in which cancer patients know ahead of time if a certain therapy will work for them or will not. So this is one step closer to personalized medicine and a world of difference for those patients. To sum up, I've described our efforts to build disease simulators. I've shown you how such a simulator can lead us to discover novel drug targets and how it can take up a step closer to realizing the potential of personalized medicine. Let me end the talk by thanking all the people behind the work. First of all, my group, especially Nir Atias, Arnon Matza, Yael Zilberberg, and Dana Silverbush. Second, my many collaborators, some of them are mentioned here. And last, but not least, the Kadar family, that by this prize recognizes the importance of personalized medicine to the future of medicine. Thank you.